All right, great. So hi, everyone. Welcome to Build. Thank you for attending this session. It's bright and early. I hope you guys had enough coffee. So today, we're going to talk about enterprise security in the era of containers and Kubernetes. So my name is Saurya Das. I'm a product manager in the Azure Kubernetes Service team. And then with me, I have Eric Skibicki. He's the principal architect at Finastra. We also have George Palma. He's my peer. He also works in the Azure Kubernetes Service team as a product manager. So in the agenda today, we have, we'll talk about the Finastra story, how they've used containers on Azure and have used various products, how they've adopted security controls that we have in AKS. We'll do a bunch of demos as he talks through all the features that they've enabled, and then we will, wrap up with, the learnings we've, had from working with each other and the impact that he's generated in his org. Now, a quick show of hands. How many of you here, have heard about Kubernetes? Great, everybody. How many of you have used Kubernetes? Okay, that's quite a bit. Good. So that's great. So the enterprise security story used to be very different when it was on-prem, running VMs and running applications. With the advent of cloud and containers, it's changed. So for the time, folks were, when they moved to the cloud and used raw IaaS or virtual machines, the security controls pretty much remained the same. With the advent of containers and Kubernetes, it's a complete paradigm shift, and a lot of the folks are quickly trying to figure out what security means in terms of when it comes to containers and Kubernetes. So we take an attempt with this session. We want to take an attempt to explain all the security controls that are there in AKS or any Kubernetes cluster that you should be looking at. The list is quite exhaustive. There is more, of course, you can do, but yeah, this is a 300-level talk. There'll be a lot of demos, like I said. With this, I'll hand it over to Eric to speak about Finastra's story. Thanks.
So today I'm here really to just tell you a story. This story is how Finastra adopted containers and Kubernetes to really drive our future strategies for enterprise security. Finastra, as you may not know, is a global financial technology provider. We're one of the world's largest financial technology providers. We have 9,000 customers in 130 countries. 48 of the world's top 50 banks use our software. We have products that range from banking cores to lending to payments and anything else that you could find in a bank. My role within Finastra is to help drive cloud strategies and build no-ops practices throughout our organization. Part of our real strategy or our real drive to adopt Kubernetes came about 2 years ago when we started a project to build an open API platform that would host APIs for the vast majority of our product lines. Kubernetes allowed us to be able to have security that was very robust, and it would allow us to have a drive that was an increased cadence out to production. Since we were already planning on using the industry standard of Kubernetes, and we'd partnered with Microsoft to host our IaaS workloads within Azure, we figured, let's see what Microsoft can do for us in Azure to run Kubernetes. About 2 years ago, the only way that you could run Kubernetes, or the best way to run Kubernetes in a semi-managed state in the cloud, was using Azure Container Services. Azure Container Services provided a simple but stable solution. You could do certain things through the managed objects in Azure that would allow you to scale up and down. The problem was after you started layering things like role-based access control and Ingress, there wasn't much else you could do. So we quickly hit a wall, at which point we needed to start looking at what else was available. The next stage for us was moving to ACS Engine. ACS Engine is an open source project that is really the underpinnings of now AKS, but then ACS. The ACS Engine project builds ARM templates, which you then would deploy out to Azure to get a vanilla Kubernetes experience on the cloud. This was great, as it allowed us to really progress and start doing things with security, but it was also bad because it was completely unmanaged. This meant that we had increased overhead at all use cases of Kubernetes in Azure. What this meant was that when we tried simple operations that worked on ACS, like scaling up and down, we would quite regularly break our clusters. When we were starting to really figure out how difficult this meant for us to run Kubernetes in the cloud, Microsoft released general availability of AKS. For us, AKS was huge. It was a fully managed Kubernetes experience in the cloud. Because it was vanilla Kubernetes and Microsoft was committed to patching upstream Kubernetes to bring fixes to Azure, it meant that it was full-featured. We'd be able to layer role-based access control, Ingress, Calico network policies, anything else that we really needed to. And we'd be able to forge an engineering partnership with Microsoft to really drive the backlog to ensure that we would be able to use it in production. Since we were committed to working with Microsoft and committed to working with Kubernetes, we now had our go-forward strategy for using Kubernetes in the cloud. What we needed to do then was figure out from internal standpoints what it would take to run those Kubernetes clusters, not in development, but in production. That meant reaching out to our information security departments and figuring out what their requirements in production were. After a series of meetings that were oftentimes somewhat cringeworthy, we came up with a pretty comprehensive list of what the requirements were to run Kubernetes in production, at least from the standpoint of traditional information security. The first of the three that I'll go over today, information security required us to have managed patching in the cluster. Now, this wasn't being done through any sort of cloud-native solution. They wanted us to actually use the existing IaaS patch processes that they had in place. These weren't cluster-aware, and in fact, we couldn't even figure out a good way to schedule patches so we didn't have cluster reboots happening simultaneously, which of course caused an outage. In addition, and this was one of those cringeworthy moments, they were actually telling us that we needed to patch the containers that were running at the time. Anybody who has run containers probably knows you don't run patches on containers. 2, they wanted us to use pre-existing hardened node and container images. These were images that would be stored in a repository managed and maintained by staff within the information security department. Because we were never really able to be sure if patches had been run on a given day or if patches were really kept up to date, because it was a manual process, this was suboptimal. We'd never know if we were actually rolling a vulnerability out to production. In addition, because it was a corporate standard image, these images would have base software installed, like antivirus. The premise being, from the information security department, you could never really be sure who was logging into a VM to do what action. On Kubernetes, when was the last time you really logged into a node? The last thing that they really wanted us to focus on was how IP traffic would be segmented. In a standard IaaS world, you have your 3 layers, your presentation, your data, and your service layer. Those are traditionally segmented, so that way you don't have to worry about crosstalk. In a Kubernetes cluster, you can be running all 3 of those layers in one cluster. So from the information security perspective, they wanted us to actually try to implement IaaS-based firewalls between services talking to each other. This wasn't really things we wanted to do. So what we came up with was a list of about 7 things that we would be able to implement that would meet those security requirements. We figured out a series of tools, the first of which, Azure DevOps, would meet the needs of CI/CD standardization and automated container hardening. The next, Aqua Security. This allowed us to build in right away that hardened container or the container vulnerability scanning. Next up, we needed layer 7 protection. We already were utilizing F5 gateways within our cloud offering, so it made sense to put one of those at the edge too. For cloud Kubernetes network segmentation, we looked at Calico, node patching on AKS managed by Microsoft, role-based governance, it was all right there. And all of this really fed in to building that no-ops pipeline that we were looking for. As I'd mentioned, the first of these tools was Azure DevOps. Azure DevOps didn't just drive our code. Azure DevOps also drove our infrastructure deployments. We built a service catalog of ARM templates and scripted configurations that we'd be able to reuse throughout all segments of our application lifecycle. If any product throughout our company needed one of these standardized components, we would be able to go out to our service catalog, anybody on our team, and they would just reuse the existing templates and configurations, and we would have a security-hardened method for deployment. In addition, because of that consistency, we were able to make sure that logging and monitoring and any audit tracing that we needed was all enabled from the get-go. All of this compounded to really accelerating our infrastructure deployments. Next up, we had to really look at how we handled the code. When handling the code, we needed to be aware of how we are building the code. Code in an instance of Kubernetes is, of course, a container. To build those containers, since we were using a standardized Java platform, we realized we could use a standardized template. Microsoft has released YAML build pipelines. Using a YAML build pipeline, we were able to create a pipeline as an artifact of code in a repository. That meant we could put an SDLC around that build pipeline and have notifications of changes, have an actual review process around our build. In addition, we could reference that as a master template that all services could use. So rather than having each individual service having its own snowflaked configuration for builds, we're able to reference and reuse. Those standardized build templates would have all of our base information security hardening profiles, code quality gating, static code analysis, open source vulnerability scanning were all included out of the box as long as you reference the master template. In addition, we showed the information security team how if we pulled from master repositories, the images we'd use for the containers would actually be patched at the source. It was continual patching. Anytime we would pull something down, we'd know that we would have the latest version of those images. This also meant that once we built those containers, we could run something like Aqua against them to determine what our whole container vulnerability profile was. Each step was gated to ensure if something failed, our build process would stop and we wouldn't be able to release that code out to production. Once again, building security in from the start. The next segment that we really had to cover was how we handled network security within Azure. To drive the security layer, we couldn't have a public cluster. That's bad practice because you don't want to have people having direct access to your clusters. You don't want to have even the chance of exiting that sandbox. So what we did is we put all of our clusters internal. The worker nodes were fully internal. And we used a web application firewall to scan and proxy all of that traffic back to the clusters. After the traffic would pass the web application firewall, it would send that traffic to one of two different sides. It would either go through the API management instance, which would apply API policies, and then route traffic through a second Ingress controller, or it would connect traffic to the web end that was in the web front end that was running in our Kubernetes clusters, and that would go through the first Ingress controller. Having multiple Ingress controllers allowed us to really segregate the traffic that was coming into the cluster and provide visibility as to what traffic was coming from where, so we could figure out better how to scale and audit what was being done in our clusters. And here's George with a demo of Ingress.
Cool. Thanks, Eric. So just for the, I think, small number of folks that did not raise your hands and are already very experienced with Kubernetes, the way that you can expose traffic on AKS today is kind of one of three major ways. The first one being by a public service. That means that you expose your application directly with a load balancer that Azure creates automatically for you, and that gets a public IP, and that's the IP for your application. More applications would get more front-end IPs in that load balancer, and each one would have their own. Now, assuming that you don't want to actually have a public service and you want something more internal, you can actually expose that with an Azure internal load balancer. In that case, same process applies. You just change that little tag, right, that little annotation there on the YAML file that says that it's an internal load balancer, and that from that point onward, no public IPs are created. The third one is the one that Eric mentioned that Finastra is using extensively. It's the Ingress controller option. And this option is very useful if you're not wanting to create one IP address for each application, or you don't want just L4, but you want more of some L7 capabilities, such as SSL termination or path-based routing, HTTP routing. kind of capabilities. And so Ingress controllers are the native Kubernetes L7 option for it. All right. What if you want actually to secure this option, or literally any of the topologies that I just mentioned? As Eric just mentioned, you could just basically drop a WAF in front of it. This could be any WAF that you're using today from any of the vendors that are out there, or it could even be an Azure native application gateway that doubles down as a WAF, right? And you just drop it in there in front of all of this, and it would just work. But for those of you that are using application gateway, you might have just raised one eyebrow or even two, because you probably know that application gateway is actually an L7. So wouldn't it make more sense if application gateway would be directly calling out and directly doing the L7 work while doubling down as a WAF? Well, we thought the same. So based on that, we came up with application gateway Ingress controller. This Ingress controller essentially is a component that still runs on the Kubernetes cluster, but instead of doing the whole L7 work like other Ingress controllers, it actually basically calls out into application gateway and does the translation between Kubernetes native Ingress resources and the ARM calls that app gateway receives. Okay, let's take a look at how this actually works. Get that there. All right, so the first thing that we're going to do is I'm going to create a group to deploy everything that I'm going to use here. And to start with, I'm going to do some nice network segmentation. So you don't need to fully follow up with all the things that I'm writing there, but essentially I'm going to create 3 subnets. The first one is the one where I'm going to deploy AKS. It's the AKS subnet with that prefix. The second one, I'm going to call it service subnet. And there I'm going to deploy basically shared infrastructure, maybe even the load balancers that I'm going to use, if any, and any other resources that I want. The third one I'm going to use to deploy my, basically my WAF, in this case my application gateway. And I'm going to segment them into different CIDR spaces and different addresses. So I'm just going to now get basically the subnet ID for the AKS subnet so that I can pass it at AKS creation time. So it's saving it in 2 variables right there. And what I'm going to do now is I'm going to create the AKS cluster, which kind of all the bells and whistles. So I'm going to create it with 113. I'm going to make 2 nodes, and I'm going to basically configure the DNS service IP, the DNS namespace, the service namespace for the services in your cluster, and as well, you might see that I'm not specifying the pod IP. So whether the pod IP gets their, where do the pods get their IPs, that they get it from the Azure subnet that I just defined, because I'm using Azure CNI. Okay? So I'm not going to wait for this cluster to actually create, as you see by the no wait flag right there. I'm going to switch to one that I already have created. But before that, I'm going to actually create the other part of the infrastructure. I'm going to create the public IP, the only public IP that you'll know in this case, and the app gateway, the WAF, and L7 that we're going to use. And I'm going to associate this public IP into it. So in this case, all the public traffic that we will receive, we want it to flow through that firewall, through that WAF, and through that app gateway. And as you see, all the bells and whistles you can configure as well from L7 perspective, like cookie affinity and everything that you want to do, you can do it right there. So let me change now to a cluster that's already created and see if it's still running and everything is well, or otherwise I need to run out of the room and cry. Let's see if the demo gods are with me. All right, still running. That's good. So how can we deploy that component that we need to do those calls to app gateway in order to configure it? So I'm going to use Helm to deploy it. And the thing I need to pass to that, if you don't know what Helm is, it's a package manager for Kubernetes that we're very much spearheading at Microsoft that makes the installation of a number of manifests really, really easy. One of those manifests is going to be this configuration file. And in this configuration file, we're going to have 2 very important things. The first one is, well, what is your app gateway? So what's the name? What's the resource group where it is? And the second one is the identity that you're going to use to configure it. Because you cannot just configure a random application gateway. That would be not good. So you're actually going to use an identity, either the cluster identity or an identity for this specific pod. So as I said, I'm going to use Helm to install this. I'm going to pass it this configuration file. And from that point onward, Helm will deploy all the components necessary for this solution to work. I already have the AKS cluster created. I already have the application gateway and WAF created. And now I'm just going to create this component that's going to link both of them together. So let's let Helm do its magic. And cross our fingers once again. Send some positive vibes. There we go. So as you see, we're bringing up the resources. They're still coming up. Let's see if they already come up. Remember, this resource that we're deploying here is only going to do this translation between a Kubernetes Ingress and App Gateway. So what does that look like? So I'm going to now deploy an application, simple application that shows basically pictures of fruit and says if they are an apple or a banana or a grape, whatever they are. And I'm going to show you, and the application is fairly simple. I'm just going to kind of an image, everything is encoded there. And I'm going to do a bit like Finastra, and I'm going to create 2 paths. Everything that comes from the public will come to that WAF, that only public IP that exists, right? But everything that is internal, I'm here deciding to create a load balancer that is internal, and I'm actually defining a static IP for it. So maybe, this is an option, everything that comes from an internal network could flow directly into that internal load balancer instead of going through the WAF, as an option. The Ingress, though, is exactly the same as any Ingress from Kubernetes that you saw. The only difference that you can inject in any Ingress out there is this annotation, so that it tells the Ingress to go and basically translate this rule, this basic Ingress rule, into application gateway, things that application gateway understands. So basically configure the backend pool. All right, let's apply all of these things and deploy the application, deploy the Ingress, and we're then going to wait for this magic component to do its work and update the app gateway for us. Right, so the web part is deployed. Now the Ingress part. And I also have a worker that is actually doing the image processing that is staying in storage. And I have a service endpoint to my storage account that is enabling the private communication. So I haven't had to do any ports opening or anything like it because I'm using a service endpoint to my storage account. All right, we're good to go. Let me see if everything is deployed. And then hopefully, if everything went well, we'll be able to test it. And if you took note of my public IP up there, you could actually start testing it now. All right, everything is running. I'm getting lucky, I guess. All right, we have an IP. Let's quickly go into the browser. And if everything goes well, there we go. The application is running. This is my application gateway IP. And the image classification is working with some failures spectacularly, I think, but it's learning. Give it some time. It will eventually get there. Okay, but this was very easy to do. So right now, let's switch back into the presentation. And Saria will guide you into, now we control Ingress. Let's see how we can control Egress for you right now. Okay, whoops, too soon. So on AKS, you can very simply control Egress like via the Azure Firewall, for example, and Saria will demonstrate how to do that for you.
Okay, sure, thanks. So let's talk about outbound traffic and inbound traffic into the cluster. So by default, if you deploy a pod, it can reach the internet and various URLs that are available out there. So one of the enterprise needs is to lock down traffic that goes out from the cluster to only a specific few that are required. If you deploy an AKS cluster, we require only a few of them, and the north-south traffic, that is. And if you can see, there are only 4 or 5 of them. The first one is the ability for the node cluster to be able to reach to the API server. The second one is all the charts or images that are deployed as a part of the system cluster or the API server are stored inside Azure Container Registry, so you need to whitelist that as well. And then there is security for app patches. For the OS patches, you need to go to ubuntu.com. And of course, there are a couple of others like login.microsoft and the management.azure.com. 2 ports need to open them, 9000 and 443. 9000 is for the tunnel gateway, for the communication between the API server and the cluster. And then port 443 is also, that is where the API server accesses the cluster. So let's go ahead and take a look at a demo that I have for Egress. YouTube. Okay, so here's a demo of Egress. What I have here is I'm going to create a group, like everything in Azure requires a group, a resource group. And I'm going to create a virtual network. This is the virtual network in which I will create 2 subnets, and both subnets, one subnet is for the AKS cluster, the other subnet is for the Azure firewall. Once that is done, let's try to create a subnet. This first subnet, like I said, is going to be for the Azure firewall that we're going to put in front that will control traffic that goes out of the cluster. As you can see, this is the firewall subnet. It's got an address prefix. So the next one is also, so I've created a public IP now. And this basically is the public IP that will sit on the firewall. And now I'm going to create a firewall. This specific firewall will sit in front of the cluster and will control traffic. Once that is done, I will associate the public IP with the firewall. The next step is to grab the private IP of the firewall. Remember, there's traffic that needs to flow from the cluster, like the overlay network inside the Kubernetes cluster or the node pool that you have, to the firewall and then to the public IP. So I'm grabbing the private IP, and then I'm going to create a route table. So what I'm going to do in this route table is create a route that defines the hop from the cluster to the private IP of the firewall. This is pretty straightforward. And then I'm going to create network rules. Like I said, the first network rule that I'm going to create is to allow ports 443 and 9000 to be open so I can communicate over them. The next one is an application rule that defines all the external URLs that you can reach out to. It's listed on this slide. It's the same 4 or 5 that we have. So it's just whitelisting them. And once that is done, I'm going to update the subnet with the route table. We just created a route table, but then the route table has to be updated with the subnet so the cluster knows how to route traffic. Once that is done, I'm going to create a cluster. And now this is a standard AKS cluster with Azure CNI. I'm defining a bunch of parameters, what network plugin to use, what network policies to use. I'm defining all the address ranges. You can choose not to select these. You will get some default values, which are exactly the same what you see here. So in the interest of time, I'll of course not create the cluster here. It takes about 6 to 7 minutes. But let's go ahead and try to get credentials of the cluster and connect to the cluster. Hopefully this will be very quick.
Fingers crossed.
Fingers crossed. Do I have access to internet?
Yeah, you should. Give it a second.
Okay. Okay, let's try to switch. I'm just going to try to.
Oops.
Okay, it looks like I don't have connection. Let's switch the connection over.
Oh, this is real demo then.
This is real demo. This is a real demo.
Threw me off with that automatic typing there.
Okay. It looks like it's trying to connect. Password is. Yeah.
Even with the connection in between. All right.
Yep, that's good. Let's try
Probably need
again.
to run the command in another shell.
Yep. You're right.
Copy paste it.
I'm going to run this command on another shell. Well,
all right.
it's good.
That's
It works.
Let's continue.
So let's try to kind of see all the pods in the cluster. So you can see there's a bunch of system pods running, a bunch of like kube proxy, metric server. Tunnel front is the one that I talked about that accesses port 9000. Now what I'm going to do is deploy a simple test pod. This is a core DNS pod. What I'm going to do is exec into the pod. Let me first make sure that it is up and running. Great, it's up and running. Let's go ahead and exec into it. So now I'm inside the cluster with the pod deployed, and I'm trying to access URLs outside of the cluster. Now, like I said, I've opened up ubuntu.com. If I am to curl ubuntu.com, I should be able to reach, right? It's pretty straightforward. I was able to. Now, if I try to reach, say, chucknorris.com, he should be able to reach everywhere. That shouldn't work. And that is how strong our security is. So that's failed. So I'm going to exit, and then going to do a bunch of cleanup.
Cool.
So what I just showed was basically restricting north-south traffic inside a cluster. Hugely important to enterprise customers. You don't want everyone to have access to URLs outside. Moving on, Eric will talk about cluster security.
So now that we've really talked about north-south traffic, we need to also look at east-west and securing our clusters as a whole. As I'd mentioned before, node patching was really one of the hot points that information security had. Because we were already running AKS, Microsoft already applied patches to all of our node pools out of the box. There was nothing we had to do there. The problem was if one of those patches required a reboot. This is where the Kubernetes community really comes in handy. The Kubernetes community is very strong. All we had to do was about one Google search, and up came the cured daemon. Cured daemon is a cluster-aware rebooting solution for patching. We deployed that with a simple Helm chart, and we had a cloud-native, Kubernetes-aware patching solution with minimal time spent. Looking at the east-west traffic, we now needed to look at network segmentation within our clusters. As I'd mentioned before, we looked at Calico. Calico allowed us to apply network policies that would segment our traffic down to the namespaces. Each one of our services was already deployed to its own individual namespace. So with that, we were able to control how traffic could flow between the pods that were running, and we had no issues. The last one, and this was one that only got answered very recently, was how do we control access to the API servers as those within AKS are public. We worked with Microsoft, once again, through our engineering partnership, to get this issue all the way to the top of their backlog. What we needed was some way of controlling that security into the API servers. Microsoft came up and said, we can build API server whitelisting. We can give those API servers a series of IP addresses that are able to communicate to the API servers. They're still technically public, but no one else can touch them. Sorry, we'll do a demo of network policies with Calico and IP whitelisting.
So we just talked before about north-south traffic. What about east-west traffic? Like you got a bunch of pods deployed inside the cluster, and then you don't want every pod to have access to the other pods inside the cluster. Traditionally, in an enterprise security, in an enterprise company, they have a large cluster and they dole out namespaces, logical isolation inside the cluster to different teams. And sometimes they don't want the traffic to flow between these namespaces. That's east-west traffic, and you want to restrict that. Sometimes there are use cases when you deploy applications, like you have a 3-tier application. There might be no reason for the backend to talk to the front end. You should be able to isolate that traffic as well. And then there are use cases where you have a namespace and you do not want any traffic to flow in or flow out of that specific namespace. So you can do all of this using network policies. So let's start with a demo. What I have here is a cluster that is already created with Calico enabled. So I'm going to show you how do you create a cluster with Calico enabled. It's primarily you provide the network plugin as Azure. If you don't provide it, it'll take it as a default. And then you define the network policy as Calico. There is another option that we have. You can do network policies through Azure native network policies, but I'm using Calico here. And once you create the cluster, you might want to, of course, connect to the cluster and then do a...
If you have Wi-Fi?
Yes, I have Wi-Fi, hopefully. So what I'm going to do here is create a namespace called Advanced Policy Demo. The namespace has been created. So what I'm going to do now is run 2 replicas of Nginx inside that cluster. And after I run 2 Nginx pods, I'm going to expose them on port 80 with an internal IP address. So now all I've done is there is an AKS cluster with Calico network policy enabled, and I've deployed 2 Nginx pods. Now what I'm trying to do is I should have access to all these pods, like be able to ping them. So if you look below at the shell, I'm going to connect to, I'm going to create a pod called Access inside the same namespace, Advanced Policy Demo. It's called Access. I'm running it in iterative mode. And then it's the busybox image. And I'm going to create a shell inside it. Okay, so now I'm inside the shell. Now if I go, just a couple, one moment. Now from that shell, if I try to ping Nginx that is running inside the cluster, I should easily be able to. So you see the body, I get a return when I do curl. Now if I do, so if I, okay, just one moment, let me clear this up. What I'm trying to show now is if I want to do egress traffic and try to, from a pod that is running in this namespace, if I try to reach to google.com, that should also work, like you see. Now I'm going to go apply a few network policies. Now this first network policy is disallowing any traffic to flow inside the cluster. It denies all ingress traffic inside this namespace. Advanced policy demo, and it says the policy type is ingress, and this tells this network policy with this definition says that no ingress traffic is allowed into that namespace. Now if I try to,
you need to enter it.
Okay, I have not run the network policy. I need to run the network policy before it can work. Now if I try to do ping Nginx, that should not work. I should time out. And I've set the timeout as 5 seconds because we don't need to wait more than that. So you see, it's gotten timed out. But egress traffic is still allowed. So if I do google.com, I will get the response back. Now again, what I'm going to do is run another network policy. Now this network policy, it allows ingress traffic, but specifically to the Nginx pod and nothing else, just the Nginx pod. The way it is done is, again, I have some metadata. The name of this network policy is access Nginx. I've defined the namespace here, the same namespace that we have. And then I'm saying match the pod with the label Nginx, and then allow ingress from any pod that is running in that namespace. I already have the access pod running, so I'm going to try ping Nginx. I should be able to ping Nginx. Oh, I have not run the network policy. It's not been applied. So now it's applied. Good, it timed out. So now if I run Nginx, it should be able to get the value back.
Cool.
So that's network policies. Maybe I have one more example of restricting all egress traffic. So this network policy, what it does is, it default denies any egress traffic out of the advanced policy demo namespace. And I will not forget this time to run this. Once this is done, what I'm going to do is, now if I do like an NS lookup on Nginx, it should time out. So all egress traffic from the pods have been restricted now. So this is how you primarily, like you can see, it is timed out. Now let's take a look at all the network policies we defined, just to recap. So there's the default ingress. This denies all ingress traffic into the cluster. Then I said, OK, now you can allow ingress, but only to the Nginx one. That's when we created this policy. And then finally, we created a third policy called default deny all egress traffic. So that's network policies. Now I'm going to delete the namespace. So that was it. OK, and then now what I'm going to do is talk about API server whitelisting. So the way this works is, as you are aware, if you are not aware, the API server of AKS has a public FQDN, which means that anybody who has access to it can ping it from anywhere, right? From home network, from office network. And then, like Eric said, we don't want everybody to have access to the public IP. So we have a feature called, it's called API server whitelisting, and I'm going to demo that to you right now. So let me go IP whitelisting. And I'm going to run the script that I have. Should be a fairly straightforward demo. So I'm going to get credentials of a already created cluster that has IP whitelisting enabled, and I've whitelisted two ranges, two IP address ranges. Now you can look that if you look at this My Machine, this client has this IP address, 24.75. Now I'm going to show the details of the cluster to you. So if you look at the API model, you should see, if you have IP whitelisting enabled or API server authorized IP ranges, you will see these two ranges. Now this range is specific to the service. So to enable IP whitelisting, what you need to do is you need to deploy a first pod inside the cluster, the node pool or your cluster, and then expose it publicly, because that's how the API server is going to communicate with the cluster, through that public IP. So you have to whitelist that. The second one is the client's IP. And this 40.83 is specifically the IP address of the Azure Cloud Shell. So if I go to the Azure portal and I open up a Cloud Shell, takes a little bit of time to load. Okay, there you go. So it looks like the IP address range has changed when I switch the network. So it changed from 40.83, which I had set before, to 40.1.12. So it's not going to work. If I try to ping it from here, it's not going to work. So I'm going to have to change it.
Right.
So let me try to whitelist actually. So I'm going to actually have to whitelist this. So if I go here, so it's 40.1.112. Okay, I don't have the cluster name here, so I'm going to have to change the cluster names. So it's going to take a little bit of time.
You can't.
It's fine. I'm going to just, in the interest of time, I'm just going to change the.
It's failed. It's the most important, right?
Yeah, it has to fail. So what I'm trying to say is you should be able to ping the cluster from only these ranges. This is the public IP inside the cluster, and this is the client that should only be allowed. Nothing else should be allowed. So if I try to ping this cluster from inside this, so this is how you actually apply the authorized ranges. You got the update command, and you got the IP whitelist ranges that you want. It's a comma-separated value. At this point, you can provide only 10. It's limited to 10. We will increase the limit. So once that is done, if I try to connect to the nodes, I will not be able to do that. That's because the IP address of this machine is 23 dot something, and that's not whitelisted. So that's my demo. In the interest of time, I'm going to switch it to one, and Eric can take over.
So one thing to note is that even though our clusters had those public IPs, prior to API server whitelisting, we were never really at any risk. All of our clusters were already secured by role-based access control. We wanted to ensure that no developer would be given access to the admin credentials on our Kubernetes clusters. So the first thing we did when deploying anything, you'll notice from the beginning slide, I talked about ACS, role-based access control, ACS engine, role-based access control. The first thing we did when deploying AKS, role-based access control again. What that meant is that we were able to use Azure Active Directory integrations on our clusters to ensure that users had a single sign-on experience when accessing and using the Kubernetes clusters themselves. In addition, we knew that we needed to extend this role-based access control all the way out to production. The problem is that in production, you need to have slightly stricter audit controls for who is accessing cluster and how they're doing it. We used just-in-time controls, just-in-time access, which is also another native component of Azure. What this meant was that when a developer needed access to use one of the production clusters, they would go out to a portal, click a button that says, please give me access, and somebody from operations clicks accept, and that developer now has the ability to reach out to those clusters and actually use them, troubleshoot, and for a duration that's just long enough for them to fix what they need to. The last part that we really found beneficial about using AKS, along with all of other components, is just the central support aspect that we received. Having the fully managed clusters meant that when we'd have a problem, we could reach out to Microsoft and say, hey, Microsoft, we're having a problem. That, in conjunction with our engineering partnership, meant that if it was an actual bug with Kubernetes, Microsoft would once again prioritize that to the top of the backlog to get it fixed. That's kind of how we pushed out API server whitelisting as quickly as we did. George?
All right, so as you saw, kind of have authentication to your API server is kind of a big thing. And the easy integration that we built in on AKS with Azure AD is trying to enable exactly that scenario. Just to quickly recap, there are two different levels that you need to worry about here. One is Azure RBAC, Azure Role-Based Access Control. Azure Role-Based Access Control controls the authorization to the Azure calls. Who can create the cluster, who can list clusters, who can create VMs at the Azure level, who can access the Azure portal. Kubernetes RBAC, Role-Based Access Control, defines who can do things inside the cluster. Create pods, delete pods, list, all these kind of actions, all right? Now, what we did is, how can you link these two together? How can you link Azure AD users and link roles that you create on AKS to do this kind of operations, right? The first thing you need to know is that on Azure, there are two roles that control the access to the cluster. These are the ones that you see there, Service Cluster Admin and Service Cluster User. There is one key difference about them, is that the admin one can pull a special kubeconfig called the admin kubeconfig that is kind of God mode. It has a special token and it will bypass anything. And it allows you to configure the cluster and do all the initial tasks. The other one will always force you to log in and provide your token and your claims, and based on that, it will authorize you to do that, whatever call you're doing or not. Let's take a look how that works, actually. All right. So I'm going to try and replicate a very simple enterprise environment. I'm going to create two groups. I'm going to create the Ops SRE group, and I'm going to create the App Dev group. Now, these can be groups that you already have on your Azure AD, and you already have completely segmented. Then I'm going to do two quick assignments. What I'm going to say is that everyone within these groups can have the cluster user role. So they can only pull that normal user kubeconfig that always requires you to log in. But now I'm going to put my admin hat for a bit, and I'm actually going to pull the admin one. So notice the last flag there, --admin. This allows me to get into the cluster immediately and start doing some initial operations, like creating a namespace for the developer team, or maybe even for the Ops SRE team, or shared namespaces, or whatever type of things that you need to do in the cluster. But more importantly, it will enable me to configure the initial roles for this cluster. The first one being the developer role. Now, this role allows access to do anything, but with a very special thing, only in the dev namespace, right? But you can do anything there. Let's now apply this role. Now you have a role in Kubernetes, but it's not attached to anything. It's just like an existing role. So you need to do an assignment, like we did with the user role on the Azure side. We need to do it on the Kubernetes side. And this is where the key thing happens. This is where the magic happens. Because this is where we do a role binding. That's what it's called in Kubernetes. And we're going to bind it to, we're going to bind that dev user role in the dev namespace into these subjects. And these subjects are a group with a very special GUID right there. And if you don't recognize it, memorize it there. B9 is actually the GUID of the group we created before, right? So we're going to apply it, and what this does is, whenever someone from this group goes into the Kubernetes cluster and tries to do an action, AKS will query AD, give me the groups of this user. And if the groups of this user has that GUID, it will say, you can do these actions. If it has multiple, it will, of course, merge the actions to what you can do, right? The other thing I'm going to do is I'm going to do a binding for the ops as well, right? But in this case, I'm not going to create a role. I'm going to use one of the existing roles in Kubernetes, which is the cluster admin role, and just map it to the ops SRE group. Apply it. All right, we're all good. So now the last thing that we need is, let's actually put someone in those two groups. So I'm going to put myself, and I'm going to take my admin hat away, and I'm a developer. And I just arrived, and I was told that I got access to this cluster. So I'm just going to do get credentials, as one does, but no admin. Notice that I did not use --admin, because I don't have access to that --admin anymore. So what I did now is I did this. I'm going to get basically an empty kubeconfig that says, you need to log in. So hopefully, if everything goes right, and actually I'm able to get my credentials, I'm going to try and execute a command, any command, with kubectl, right? In this case, I'm going to try directly to create a pod and on the dev namespace, which is something I should be able to do, but I cannot do it without actually announcing who I am. So for that, I'm going to have to log in. And if you know if you worked around Azure AD and Azure for a while, you know this flow, right? So this is the actual device flow that you've probably used several times. Have MFA, have everything there. It's backed up by Azure AD. So I'm just going to paste the code, select the account I want to log in with, and fingers crossed. All right, it's good. And now I'm logged in. So now I'm going to get a token for myself. I'm going to send it to Kubernetes, say, hey, this is me. I'm George. Trust it's me. This is the token. And then Kubernetes will say, OK, I trust that you are you, but I don't know what you can do. So I'm going to query AD and see what groups you have. And it will see that I'm a dev, and I can do this. So I will be able to create the spot, and it is created right there. But now I'm saying, OK, I'm a dev. I actually have no idea of what I'm doing in this case. So I'm just going to get pods from everything. No resources found. Of course, I cannot do anything like this. So now if I actually add myself into the ops SRE group, I would basically add myself as an admin at that point onwards. And the cool thing about Azure AD at that point is that you don't actually need to relog in or refresh the token or be afraid that once you remove permissions, you actually are going to have to get the token back while the token is valid. Does the user still have permissions? No. Because of this additional flow that Kubernetes has, the AKS has, that actually queries the groups every single time, because you updated the groups and you updated the permissions, this will be completely transparent in the background. All right? So with that, I'm going to swap to 1, please. Listen to a bit of, yep, so I'm already in members in this case, which makes sense because I was an admin before. So we heard the feedback from our partners and customers saying that they would like to have the capabilities to essentially apply policies across their environments. Apply policies to Kubernetes clusters and apply policies to all of their Kubernetes clusters. And this has been traditionally hard because the way that Kubernetes applies policies are either via a number of resources, pod security policies, then some things like admission controllers. And folks want to do things like, I want just to restrict where my images come from. I want to make sure that they all come from my whitelisted registries. So we've been working hard on Azure, and we're happy to announce Azure Policy for Kubernetes, which is basically a way for you to use Azure native policies that then get translated into Kubernetes policies, and you have a resource there that is gating what you can do in the cluster. We already have 10 policies created and loaded for you that you can use, and I'm going to demo one of this right now. The cool thing about this service is that you can actually apply it to the whole subscription. So you don't need to apply one by one. You can apply to all your clusters. So let's take a look at that. So what I'm going to do here is I already have a cluster created, completely empty. This works with any Kubernetes cluster that you already have today. What you need to do is, I'm going to change to it, of course, and I'm going to enable the policy add-on. It's as simple as using AZAKS enable add-ons. And now I'm going to jump into the policy blade to show you this policy at work. So I enable the add-on, so that means Kubernetes now supports Azure policies. Now I'm going to jump into the Azure policy blade, and I'm going to go and assign a policy. And that is as easy as doing here, assign policy. See well? Yeah. You select the scope, so I could leave it as my subscription, right? You can put some exclusions, some resource groups or resources that you want not affected by a policy. And the one that I'm going to use to demonstrate to you guys is the one I was talking about. It's the one that I want to limit where I can pull images from. So I'm going to whitelist a specific registry or number of registries, right? So this immediately populates. And then you have one parameter to say, which is a regex expression to define which registries you want. We have an example right here. If you want to whitelist all the Azure container registries, you basically use this policy. I already have one created and applied. I'm going to show it for you. It's exactly the same, and I already added my own registry. So it's the same policy, and I already added my registry right here. So if all goes well, if I try to use the task pod that's, we used before, that CentOS pod that was coming from God knows where. I have no idea where he put that from. Let's see. Hopefully it's not from my registry because I don't have it there. So I'm trying to apply. And of course, it denied. And it's denied as expected because it's coming from God knows where. Definitely not my registry. But if I actually try to run an image from my registry, and as you see, the image is coming from that matched registry right there, this totally works. And it's not matching, it's matching the exact registry because that's exactly what I said. So if I try from another one of my Azure registries, this will still not work. If you really quickly want to change this or edit this, it's as simple as, oh, I want to add another registry. It's totally fine. You just use native regex, and you do something like this. And there you go. You save, and now you can pull from both these registries in case they are yours. Okay, switch to there. So really quickly, we went through, really quickly, in 1 hour, we went through a lot of security controls. As Sorry mentioned in the beginning, these are by far not the only controls that you have. But there were some that are part of Finastra's story and that we found very, very relevant to showcase as a success case. We saw things from securing north to south traffic, securing Ingress traffic, securing egress traffic. We saw how to secure east to west traffic, traffic between pod 1 and pod 2 with network policies. We saw how to control who can access the API server with IPs, whitelisting, and with Azure AD. And we also saw how we can make sure that every user has only the minimum permissions that it requires to operate.
OK. So very quickly, next slide. OK. So very quickly, we wanted to touch upon what we learned from working together. So in Azure, we are very customer-centric. We work hand in hand with customers to roll out features, provide them preview features, collect feedback. And from all of this, what we've built is we built a set of best practices. This is very fairly new technology. Not a lot of people know about containers, let alone best practices. So we worked with Finastra and other companies to come to understand what is it that everybody needs to secure their infrastructure, their applications, and we've all documented all of that. So go ahead and talk a little bit about how you've gained.
So I think what we really took away from our interactions with Kubernetes and containerization is that we need to ensure that security standards are implemented as early as possible in an application's lifecycle. Once you're implementing things in development, when you push those same standards all the way out to production, you've met them everywhere that you need to run your application. We also learned that really one of the other key facts was all of our teams needed to have knowledge of what it meant to actually operationalize a piece of software. We can't have a developer who has no idea what it means to run something in production, throw something out in production, because then your software just breaks and you'll have a demo that fails on a key day. So the 3 impacts that we had as Finastra trying to really build out this information security process was increased visibility. First, increased visibility meant at all stages of the lifecycle of our application, everybody was able to see exactly what we were doing. All of our artifacts for deploying code, doing releases, for building, for creating the infrastructure were all in a repository. All of those were surrounded by SDLC practices. And every single one of them had auditability, and you could really see what was happening. All of those then led to an increased cadence throughout our application's life cycles. We could deploy out to production faster because there were less people involved at all stages, clicking buttons or approving manually or having to go out to cab. The last thing that we really noticed was we had increased collaboration. Once we started bringing information security directly into the loop, we were able to see them joining our morning meetings and understanding what was actually happening. For once, we would be able to talk to information security as if they were part of our team, and that really helped us approach enterprise information security in the age of containers.
Thank you very much. We're going to open for questions now. If you
have exactly 30 seconds.
Yeah, go.
It's brilliantly timed. Yeah, so there is a resources slide. It talks about documentation of how you can do it.
So everything we did here is documented.
There's more. There is a whole security section. If you go to AKS documentation, there are how to do things. There is best practices. Anything? Any questions? We are here.
Yep, at the end, and feel free to start in the
Thank you for your time.
Seconds. Thank you so much. Hope it was useful.
Enjoy your day. Thanks.